Hi, welcome to this lecture. We will be talking about physical vapor deposition techniques, and in physical vapor deposition techniques there are three: 1 thermal evaporation, 2 e-beam evaporation, and 3 sputtering. Now let us go one by one and understand what each technique holds for us and how to use this particular tools, that is thermal evaporation tool, electron beam evaporation tool, and sputtering tool to deposit metal, semiconductor and insulators. So, as I have told you earlier that we have also a lab component included into this particular course, and thus each tool that I am going to talk here in terms of PVD, which is physical vapor deposition, we have recorded it as well for you. So, let us go to the first slide, which is an empty slide, and understand exactly where we are going to use it. Okay. So, let me draw a silicon wafer cross section. So, this is our silicon wafer, right. Now, we have seen how silicon dioxide can be grown using silicon using thermal oxidation on silicon wafer. So, we have thermally grown oxide, this we call as a SiO2. Thermal oxide can be two types, wet oxidation and dry oxidation. And the next step after this, if I want to deposit a metal onto this particular oxidized silicon wafer, then which technique I can use to fabricate or to deposit, right, this metal on silicon. So, what is the technique that we have to see, and that is what we call as a deposition technique. Here we are depositing. What I have used word for silicon dioxide, I have said that we are growing, right, growing SiO2 using thermal oxidation technique. Right, you understand the term growing. Now, what term I am using right now is depositing. So, now we are depositing a material onto the oxidized silicon substrate. Here we have used term called, so let us say this is aluminum, okay, term called deposition, aluminum deposition, silicon substrate, SiO2 as an oxide layer. The reason of oxide layer on silicon is to avoid any short circuit with the metal layer that we are depositing using one of the technique. Now, when I say one of the techniques, then it can be thermal evaporation, electron beam evaporation and sputtering. Okay. So, today's lecture we will look into the thermal evaporation, and as the name says, there would be a thermal energy that is used to evaporate a material of our interest. So, these two drawings shows the source holder, okay. On this we will load the source that we want to evaporate. It can be beads, it can be chunks of metal, it can be wire that we can load onto this particular coil, right. This is our source. Which one? The one in blue color is the material for deposition. So, we say source material, okay. This one is our source material. Now, the term thermal, how we justify the term thermal? So, we apply, so this source holder is a metal, always a metal, alright. Source material can be semiconductor, can be metal, can be insulator. There is a limitation of thermal evaporation that we cannot deposit insulator, that we will understand in some time. But right now, the way to evaporate this particular source material is applying the voltage across the source, across the source holder, or you can say across the source. Now, if you apply a voltage, this is a metal, what will happen? The current will flow through it. When the current flows through the source holder, there will be I square R heat. This we also call as a Joule heating. Now, when you apply a current and when there is I square R heating, the material which is loaded onto the source holder will start melting. Why? Because there is a heating. So, this material will start melting, and if you keep on heating, it will start evaporating. Okay. Now, once it evaporates, where it should go, is not it? So, it will coat the entire chamber. Now, from where this term chamber comes, right. So, let us see this one as well. Why I am deleting this is so that I can draw a chamber for you. Okay. So, first let us redraw the connections. Okay, here and here. Now, let us draw a chamber. Okay. This is a chamber. This is also a chamber. What is the difference? Nothing, only that here we have used a coil, this one, and here we have used a boat. Both are source holder. Okay, both are source holder. Now, what we do is we load the source onto the, we load the substrate onto the substrate holder. So, source and substrate. Substrate again we know can be metal, can be semiconductor, can be insulator, right. Like polymer we can use as substrate, silicon we can use as substrate, glass we can use as substrate. So, we can use a coated film as a substrate, right. We can use anything as a substrate, and the way the substrate can be defined to understand is the material that we use on which we are going to deposit different films. So, to pattern it to finally realize a device, alright. So, that is our substrate. So, going back to the schematic, this is a substrate holder. Now, let us load the substrate. For us, you have seen silicon in one of the lectures. I will load silicon wafer. So, one silicon wafer and second silicon wafer, here also one and second, and then we connect a pin so that it will not fall, it will not fall. So, this is our silicon wafer. So, I write down silicon wafers here, correct. Let me write down silicon wafer. Here also this one and this one are silicon wafers, alright. Okay. Now, next thing is that I told you that this melted source material, right, this melted source material will evaporate and will start coating the wafer, it will also coat the walls. It will also coat the walls, both sides, and also other area of the chamber. You see, while doing so, the metal starts depositing onto our silicon wafer. The metal will start depositing onto a silicon wafer. All right. So, you can see that the atoms would have no time to rearrange itself, because it is so fast, the technique is so fast, atoms would not have enough time to rearrange itself. Now, if I say that when we are melting this material, which is our source material, using thermal evaporation, and the deposited film, which is our aluminum deposition that you are seeing here, is 1 micrometer. 1 micrometer is how many nanometer? 1000 nanometer. How would I know it is 1 micrometer? So, we require another tool that is integrated, or it is inside this particular chamber, and that tool we call as quartz crystal monitor, QCM. What do you call? Quartz crystal monitor, QCM. All right. This QCM works on the principle of piezoelectric. So, what is piezoelectricity? When you apply a pressure, there is change in voltage, or when you apply a voltage, there is change in pressure, right. So, that is the piezoelectric effect. Now, this QCM is used because the material that we are evaporating will also get deposited onto the QCM. See, it gets deposited everywhere, I told you, right. Maximum deposition is here, maximum. The reason is, if you have if you know the basic math, right, you will understand the cosine law, that cosine law will come into play, and you will understand that the maximum deposition occurs when you load the wafer at certain angle with respect to your source material. So, the question for you is, why we are loading exactly at 90 degree or whatever you want to say compared to the source material, or any other degree, 45, 180, it can be any degree, which is the best angle at which we would get the maximum deposition. So, that is our homework. All right. Now, what we do? Next thing. So, the quartz crystal, like I said, the material can also get deposited on a quartz crystal. When this happens, the quartz vibration would change, the frequency would change, and that is already programmed to understand what is the deposition rate, which is given by angstrom per second. So, based on the deposition of the material on the QCM, we can see the corresponding change in a display in terms of angstrom per second. So, that is how we can understand when to stop the thermal evaporation as soon as it reaches 1 micrometer, because here in this case we have taken 1 micrometer as the thickness of our metal, which is aluminum. But the question comes as that if you apply a voltage and the current starts flowing, how will control at what time the evaporation should start, because as soon as this melts, the material is loaded, it melts, it starts evaporating, is not it. So, we need to first understand that the material is completely melted, and then only we should start evaporation. So, there is one more tool within this one, which we call as a shutter. Okay. This is a metallic plate, it is a metallic plate which is between source and substrate, you can see, right, which is between source and substrate. What we call this as a shutter. So, let us SHUTTER, shutter. Okay. This, the role of this plate is not to let the evaporation reach the silicon wafers or a substrate until and unless it comes out of the way, right, between the source material and the substrate. We can only remove the shutter when we want, when we see that the material that we have to evaporate is completely melted, like this a melting is done and now it is ready to evaporate. So, then we can remove the shutter from the path, like this, right, so that the material will start evaporating. When we remove from the path, right, then what will happen? Shutter is out of the path, it can be on the side, like this, right, and then it can start. So, just to, because we have less space here, I am not drawing the shutter anymore, and you assume that the shutter is now moved out of the path from the between the melted material and the substrate or source and the substrate. So, when you do so, the evaporation will start, alright. So, this is your current I and this is our deposition. Okay. Now, the next thing is there is something called mean free path, mean free path. We need to have this mean free path high, so that when the material which is melted, it evaporates, it will not collide with the molecules present in the atmosphere. So, how long this can travel before the collision happens with the molecules, right, how long this melted material, right, that travels to the atoms can travel to the substrate before colliding with a molecule present in the atmosphere. So, that is a mean free path, right, how long it can travel. Now, to increase the length of the mean free path, so that it can travel without collision and deposition becomes better, we had to create vacuum. Okay, we have to create the vacuum. Now, vacuum can be created using vacuum pumps. So, we require vacuum pumps. There are two pumps that are used in this thermal evaporation. I will write down here. Primary pump and secondary pump. Okay. Primary pump is generally rotary pump. Rotary pump. Secondary pump can be oil pump, oil based pump, can be turbomolecular pump, or can be any other pump that can help us to improve the vacuum. Primary pump, the rotary pump role is to get vacuum about 10 to the power minus 2 to 10 to the power minus 3 torrs. The secondary pump role is to get us vacuum from 10 to the power minus 4 or greater than 10 to the power minus 3 all the way to 10 to the power minus 7 torrs. Now, torr, not torrs, torr. We also give unit as millibar, Okay. So, that means that we require 2 pumps, primary pump and secondary pump, that is there. Because we deposit the material in the presence of vacuum, these physical vapor deposition techniques, whether it is thermal or e-beam or sputtering, is also called vacuum deposition. Okay, is also called vacuum deposition. All right. Next thing, if I say vacuum, that means there should be some gauge that should help me to know what is the vacuum. That means, is it -2 or -3 or -4 or -5, whatever the torr may be. So, I require 2 gauges, one for which is called as Pirani gauge and second which is called as panning gauge. Pirani gauge and panning gauge. Pirani gauge is used for vacuum in order of -2 to -3, panning gauge is used for vacuum of order of -5 to -6. Okay. So, these things are easy until now. Now, we have deposited aluminum, okay, using what? Thermal evaporation. So, what can be the limitation here? Can you think what can be the limitation here? The limitation here of this particular system is that we have to rely on applying the thermal energy to the source material, so that it gets melted and starts depositing. That means that my melting point of source holder should be very high compared to melting point of source material. Melting point of my source holder should be extremely high compared to melting point of my source material. When this particular case is not satisfied, that means that what I mean is that the metal that we are using here, and let us say here we are depositing aluminum, then it is fine because melting point aluminum is really low. But let us say instead of aluminum I use silicon dioxide. Instead of aluminum as a source material I am using silicon dioxide. Silicon dioxide melting point is extremely high, and then we cannot, what happens is the because silicon dioxide melting point is extremely high, this will be melting point of source material or source holder will be approximately equal to silicon dioxide. That means the source material will also start evaporating, the source, this will also start evaporating, and that is what we do not want. We only want the material loaded onto the source to evaporate and not source holder itself, is not it. So, that is a limitation, that when the temperature or melting point of the source material is equal to or close to the melting point of source material itself or source holder material itself, source holder material is very close to source material melting point, we cannot use thermal evaporation. Okay. So, to overcome that there is another deposition technique, but let us now focus on few slides which will show you different kind of deposition system, and then we focus on thermal evaporation for this particular lecture. So, let us go to the next slide in which we will see the different kind of systems. So, on this slide you see 3 systems, 1, 2 and 3. Okay. And one is electron beam evaporation system, and another are thermal evaporation automated and semi automated, or you can say manual and semi automated system. So, in general physical deposition methods or physical methods produce the atoms that deposit on the substrate, and we have 2 techniques, evaporation and sputtering. In evaporation we have thermal evaporation and e-beam evaporation, which is electron beam evaporation, and then we have sputtering. This process is also called vacuum deposition because the process is usually done in a evacuated chamber, we have seen in the previous slide. Generally PVD is used for depositing metal. Dielectrics can be deposited using specialized equipment. However, there are a lot of materials in which the melting point of the source material is less than melting point of the source holder, then we can use PVD without any worry. Now, let us understand the what are some of the things within this photograph. Okay. So, I will try to explain it to you. This one is a view window. Viewing window. Okay. From this we can see the substrate and the source itself. This one is to change the substrate, like if we want to have aluminum, then we want to deposit, let us say gold, right, then we want to deposit titanium. So, can be one substrate or two substrate or three substrate or four substrate. So, this is a knob, for changing the different kind of material. Can we have two different or three different source material, okay, not substrate. Substrate remains in the top, these are source materials. So, we can select any source material depending on which material you want to deposit onto the substrate. Now, this is a gauge, right, this is a gauge, Penning gauge or Pirani gauge, I am not sure from this particular figure, but one of the gauge, Penning gauge or Pirani gauge. Why I am not sure, because there are two gauges. If I see the second gauge, I can tell you which one is this one. This is a door handle. So, open the vacuum. So, not this one, is it? No, not this one. This is not a door handle. I will show it to you where is the door handle. This one is a door handle. For chamber. Okay. So, when you purge the air to kill the vacuum, you can use the door handle to open the chamber. Okay. Now, let us come here, you can see this red color display, this is your thickness monitor, quartz crystal monitor or thickness monitor, generally gives the deposition rate in terms of angstrom per second. This one applies the voltage, is a variac. Okay. This one shows the current in terms of amperes. So, you can say it is a current meter. Okay. All right. And then there is a vacuum pump and another control electronics, right. Now, let us see this particular figure. Here we have two viewing windows, window 1 for substrate, window 2 for source. We have a motor for rotating, we have display, here and here, then we have electronic control system. Electronic control system. This is on off switch, okay. Then back side is a connection to the high vacuum pump, or what is the high vacuum pump? This vacuum pump can be turbomolecular pump. Again there is a gauge for measuring the vacuum. Let us come to this particular system, and then so here why we call this as a semi automatic is because we can load all the parameters. For example, I want 1 micrometer thick metal, then what will happen, this shutter will close automatically as soon as 1 micron is reached, alright. the deposition rate of the material can be, so we can say I want to deposit aluminum. So, automatically the voltage that is required to heat the aluminum will be given to the boat. So, it is like a semi automatic, because we have to feed the information and then it will happen. Again we have to kill the vacuum by purging the air and we can open the chamber, that is why we call as a semi automated system. If you see this system, this is the turbo pump, this is a viewing window for substrate, this is the viewing window for source, this is the on off switch, this is the display, okay, display, and here this is the thickness monitor, these are the gauges, one gauge I can see here, one is on the back side. This is for rotating the substrate. Why you have to rotate the substrate? Because if you rotate the substrate, the deposition becomes uniform, for uniform deposition. Then there is a control electronics, right. And then this particular tool is not a thermal evaporation, but a electron beam evaporation, and we will see in one of the lecture electron beam evaporation. Okay. So, yeah, so this is what it is in this particular slide. Now, let us go to the next one, and as we already know, let us read once again to make sure what I have told you and what is written matches, and also is helpful that when we read again and again we remember it, right, we memorize it. So, in evaporation techniques of physical vapor deposition, a vacuum chamber is pumped down to less than 10 to the power minus 5 torr. Evaporation atoms from the source condense onto the surface of the wafer. The heater can be resistive type, generally tungsten filament is used and it heats up as current flows, either filament like I said coil, or we can use a substrate or source holder like a boat. Amongst the evaporation technique, the popular one is electron beam evaporation system, in which high energy electron beam is focused on the source material in crucible using magnetic fields, and we will see this how this electron beam can be focused on a crucible. Alright, right now let us not worry about this particular sentence. Last is, depending on the method of evaporation and hardware, evaporation techniques can be categorized as thermal evaporation or electron beam evaporation. So, that we know. Now, let us understand mean free path. I told you mean free path is given by lambda, and it is nothing but the average distance a molecule travels before it collides, right. When we melt it, it will travel towards the substrate, it collides with what other molecules in the atmosphere, in the air. So, we require vacuum. So, in other words, after melting, how far the vapor travels in the chamber before it hits a residual gas molecule, and that can be given by this equation, lambda equals to kT by under root of 2 pi p d square, where T is absolute temperature of the chamber, D is gas molecule diameter, P is pressure, and K is Boltzmann constant. So, let us take an example of mean free path calculation. Suppose a nitrogen gas molecule whose diameter is 3 angstrom, okay, D is known, and temperature of chamber is 300 Kelvin, okay. So, T is known. Calculate the mean free path of the gas. Okay. Now, we know K is Boltzmann constant, right. So, it is easier for us to put the value. We have D, we have T, we do not have pressure value. So, let us assume that when this kind of things are there, we can assume pressure of -6, -5, depending on -6, -5, the overall result will come differently. If we consider P equals to 10 to the power -6 torr, then if we place all the values in the equation, we get lambda of 78 meters. That means the gas molecule can travel for 78 meter without any collision with other molecule. Let us understand the heated evaporation sources. What are different kind of sources? There can be tungsten wire sources, there can be refractory metal sheet sources, there can be sublimation furnace sources, can be crucible sources. Depending on what kind of material you want to evaporate, you can use different kind of sources as shown in this particular schematic. For example, we can use tungsten wire for a crucible, or we can use tantalum or molybdenum when it is a refractory metal, or we can use selenides or sulfides or some oxides as a pellets when it is sublimation furnaces, or we can use Al2O3 and graphite if it is refractory material, right. Sometimes higher frequency induction rather than resistance heating is also used. So, instead of just resistance heating, you can use high frequency induction heating. So, coming to thermal evaporation, it relies on thermal energy applied to a crucible or a boat, right, which is here, as you can see here in this one, to evaporate atoms, and these atoms will evaporate and deposit onto the wafers. Surface reaction usually occur very rapidly, and there is very little rearrangement of the surface atoms after striking. Thickness, uniformity and shadowing by surface topography and step coverages are the issue. So, thickness, because you have to be very particular about when to close the shutter, uniformity, and then step coverage. What is step coverage? Suppose I have the silicon wafer, and on silicon wafer I have a material which I have pattern like this, okay. And how we have pattern? Using photolithography, which is one of the technique we will see in this course as well. So, this is silicon, and let us say this one is our silicon dioxide. Now, if I want to deposit a metal, what will happen? You know, the metal will get deposited uniformly, more or less, onto this area, onto this area, okay. This is our metal on silicon, but this area will not be covered that uniformly. This step coverage is poor in case of thermal evaporation. This particular slide shows a shutter here, electrodes for applying voltage. This is 4 source, 1, 2, 3 and 4. 4 different sources can be operated using the thermal evaporation technique. So, we can have different materials or different bolts loaded onto the material. This further a zoom in view from within the chamber, right, how source can be loaded, right, between these 2 electrodes, between these 2 electrodes, between these 2 electrodes and between these 2 electrodes, alright. So, we can have 4 sources, right, 1, 2, 3, 4 and 5 sources in fact. So, which we can 1, 2, 3 and 4. What's wrong? Yeah, okay, if there are 4, I am really sorry about this. As you can see, there are 4 sources we can load. Let me write on here. This is 1, this is 2, this is 3 and this is 4. 4 sources. So, one boat here, second boat here, let us say coil here, and we can load 4 different materials onto this particular source. Okay, all right. So, if you want to deposit an alloy, right, and if you want to understand what is the binding energy of materials, right, then you understand that binding energy of alloy is different than binding energy of the atoms in a metal. And if you consider A and B as 2 different metals and AB as an alloy, then the activation energy of AB bond is different than the activation energy of only AA or BB bonds. So, metallic metals can be considered as a solution of the 2 materials, or that means mixture of 2 different materials. Partial pressure of A in AB at temperature T is not equal to partial pressure of pure A at T in PA LS 0. So, similarly for B, partial pressure of B in AB is different than partial pressure of pure B. So, if you want to find out the flux ratio from the PA and PB equation, then we can find it out that it depends on the atomic weight of B and A respectively. It also depends on the partial pressure of the chamber, and it also depends on what is the bond activation energy of each material or metal. So, the vapor pressure as well as film composition depends on temperature and properties of the material. So, in case of alloy, it is difficult to use thermal evaporation, we have to go for two source evaporation techniques. Alright, so here we will end the thermal evaporation class, and in the next class we will look at the electron beam evaporation. Till then you just look into the slides. If you have any question, you can ask us in the using the NPTEL forum. Till then you take care, bye for now.